In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice, a flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons. These creatures thrived in the distortion of space-time, causing chaos and disruption. The world needed a hero, and Miller was ready to answer the call. With his flute in hand, Miller played a tune that echoed through the cosmos. Each note, a shot of pure ether, struck the Einsteinian demons, dispelling them back into the void. The world was saved, not by a warrior, but by a musician, a scientist, a man with a flute. Remember, in this universe of wonder and mystery, sometimes the most unlikely heroes make the biggest impact. Keep your mind open, your heart brave, and who knows, you might just find the ether within yourself. So here's to Dayton Miller, the flute ether master. His melody still resonates, a testament to the power of harmony in a chaotic world.
Which is my main contention against them, but whatever. So, Alan, you ready?
He can't have a breakthrough.
Yo, I'm back.
That's
Intro
true.
is
That's
done.
true. And if what you say is true, then that's cool too.
Oh, it won't let me video share if there's more than 25 users. All right. X amount of people have to leave. I'm just kidding. I'm going to just...
Well, we can just run it in the stage. You want to just pop
Yeah,
up
you
the
want
stage
to do
real
that
quick?
instead. That'll fix that problem immediately.
Yeah, but I like the element of everyone being able to just talk whenever they have a question at the end of a slide. It's not that big of a deal.
Well, we could bring a lot of people on the stage. Like anyone who thinks they may want to talk could just jump up, and then therefore it's kind of just like a smaller VC, but it does allow you to share. Because there may be a lot more. I mean, it's probably going to be above 25 this whole time. I'm thinking I just tagged everyone as well. So, I mean, it might get up to 40, 50, 60 in the VC. So if you want to be able to share that way, it's an option. It's up to you.
Yeah, it should be all right. Screen one. All right.
Where's the stage? Oh,
Just made a stream.
Yeah. Well, okay. Yeah, we'll just run it here. I'll share that on the live stream real quick here.
Yeah, cool.
All right. Yeah, ready when you are.
Cool, thank you. All right, so this is Relativity of Simultaneity and the Sagnac Effect, an Ether Cosmology presentation by your boy SpaceAudits. So we're going to be going over the principles of relativity and where they apply, and then we're going to look at the Sagnac Effect and see if relativity theory provides an adequate explanation for that measurement. So here we go. So before we begin, I'd like to start every presentation now with two concepts, kinematics and dynamics. If you remember nothing from this presentation, remember these two things. Kinematic means measurement. You'll see some equations here that govern kinematics. These are all describing change in distance over time based on velocity, right? This is how you find velocity. Equation number 3 here is missing a t squared at the end. It's a visual bug. Everything else is correct. But anyway, the point here, though, is kinematics means measurement without causal mechanism, right? Just predicting motion based off of previous patterns of motion, right? No factors for, or no accounting for actual forces, right? And then dynamics would be actual predictions based on real forces, right? So kinematics and dynamics are two separate things. All right. And let's see, next slide. Okay, so here we have the speed of lay derivation from Maxwell. We have 1 over the reciprocal of epsilon times nu, or epsilon times mu equals c. So what they're saying here is that the propagation rate in a vacuum is approximately 300 million meters a second. So they've got their metric for how they're defining distance propagation based off of electromagnetic induction, right? All right. So next up, we're told one of the many hurdles of history is that relativity theory was the only theory that could merge Maxwell's equation with Galilean dynamics In other words, applying motion to Maxwell's equations. And we're told that through this, the story that we're told essentially is that special relativity with the introduction of the variable time in the XYZ coordinate system, that additional variable time allowed them to describe motion, because what is motion but change over time, right? All right, so Einstein has a particular flavor of how he defines time, though, in his theory. He defines proper time as the time in the moving frame, right? And then he defines the stationary frame as coordinate time. And the distinction he's trying to set up here is that, all motion is relative, and that in order to be existent, really, you have to be in motion relative to something. So what he's saying there by defining proper time is that the motion frame is the frame of importance, and the stationary frame, being coordinate time, is just some arbitrary, whatever frame, right? Is the way that he wants you to look at it. But Hertz came along and introduced time as an absolute, and then proper time, in other words, like the time in the moving frame, as coordinate time, right? So a differential from the absolute gives you the time for the motion frame, and everything is restored. Everything's fine. There's no issues. So that's one of the many stories that we're told, is that without the introduction of special relativity, one couldn't even begin to even use Maxwell's equations or whatever, the kind of stuff they spin. But it's patently false, right? It's literally the same thing, but instead of two differentials, it's just one's an absolute, and then the other one's a differential of that, right? So just breaking a little piece off to figure out the difference. All right. Okay, next one. So some experiments leading up to relativity theory are Fizeau, Arago, Airy's failure, right? Experiments that were using light to detect the motion of the Earth, and some experiments using water or a moving media to measure the translational speed of that moving media relative to the speed of light, relative to that induction rate that was derived earlier, because this is going to give them this rate of induction here is going to give them the ability to make predictions of velocity based off of this number. All right, so we'll come back now. All right, so these experiments were done, and they gave, what they say is a null result for providing evidence for the velocity of heliocentrism. And to rectify this, in 1905, after the Michelson-Morley experiment, which we'll come back to here in a second, but after 1887, that was like the final straw for experimental proofs of Earth's motion. They really didn't know what to do. There was, conclusive evidence of null results. So insert 1905 with the special theory of relativity, which says that as the consequence of the constancy of the speed of light, an observer in motion will observe events that are simultaneous, different from an observer who is stationary. So they'll make two different observations. Now, of course, we know that there's relative motion, relative Doppler shift, for example, right? But we know in reality, say, for example, if these two lightning strikes, if they strike at the same time, let's say they would send a signal to a bomb that would go off, right? Now, we know that if the lightning strikes at the same time, somehow, let's just say somehow you could time this so that they're synchronous. If they strike at the same time, that bomb is going to go off regardless of if that observer on the train is in motion, because he sees the signal on the B side first because he's moving towards it, right? Versus the stationary observer who would see them simultaneously. Well, there's no discrepancy in reality, right? We all know that the events happened, that the bomb would go off. So there should be no question of the principle of relativity of simultaneity, because this, just that example right there shows you that relativity and simultaneity are not two terms that can be added together to make a cohesive worldview. Because you can either be, if you're simultaneous, you're not relative, right? All right, so here we have a look at the Holy Scriptures from On the Electrodynamics on Moving Bodies from Albert Einstein. And here he's saying that, we attempted to discover the motion of the Earth relative to the light medium, couldn't do it, can't be done, blah, blah, blah. So maybe there's no idea of absolute rest, which is where we're going to get into the idea of defining proper, like you'll see the logic behind defining proper time and proper distance as the moving frame, because, there's no such thing as rest. And if you're important, right, you're in the moving frame, so to speak, would be the kind of the way to look at it. So anyway, he suggests here that based off of Newton's equations, where they hold true in inertial frames, any frame that Newton's equations hold true, so will the special theory of relativity. And he goes on to say that so that's the first postulate, right? That all inertial frames are equally valid and that these equations will hold true in those frames. And then secondly, he postulates that the propagation rate of electromagnetic waves in a vacuum is constant at 300 million meters a second, roughly. And it's independent of the state of motion of the emitting body. And right here, it doesn't appear like he's saying anything new or anything, right? Because everyone knows that the speed of a wave is measured relative to its medium and the velocity of the observer, right? The motion of the observer. So what does he mean by this? Well, he means if you're in relative motion, right, with that emitting body, you're not going to be able to measure your velocity against there's going to be no change, right? Because it's a constant. So he's putting this forward, of course, to explain all these experiments that were done that gave a null result for the velocity of Earth. And then he goes on to say here, we don't need an introduction of a luminiferous ether. So this comment in particular is describing the physicality of the medium, right? So the ether wasn't just an abstract mathematical concept that provided a reference frame where they could use it to measure all motion relative to it. It was also postulated to be a material media that was necessary for electromagnetic propagation. And so he's saying here that not necessary, it'll hit up that vacuum speed. There's no need for an ether. And then he goes on to say that we don't need an absolutely stationary space to be provided with special properties where we'll assign velocity vectors for electromagnetic propagation in that empty space. So what he's saying there is that for bodies in motion, and when there's electromagnetic propagation going between them, if they're going at the same speed, right? If the motion is rectilinear and uniform, then because of the constancy of light, you won't be able to measure a velocity, and there'll be no discrepancy. And otherwise, you would be measuring velocity with respect to some point. And he's saying that's not what we're going to do here. So we're not going to be able to invoke absolute space for measurements with electromagnetic propagation, in short. Okay, so then he continues on here to lay out the kinematics of the theory. And I already talked about time earlier a little bit, but we'll just give a quick recap here. So he's saying that time is not an absolute in the sense that if I said, meet me here at 7 o'clock, everyone in the entire world would instantaneously know what my 7 o'clock is. What he's saying is that this is like a local phenomenon between two people, in their relative motion state. So 7 o'clock, if he says that, if he says, meet me at 7 o'clock to a coworker, well, that guy's going to know what 7 o'clock is, right? Their relative systems are in the same spot, like they're aware of each other, right? So they're in the same time zone. But if he said it to somebody else, well, is it my 7 o'clock, your 7 o'clock? So that's what he's putting forward there, that there's no absoluteness to it. So you would always have to think of it through this lens of relative to some coordinate time, right? Just some arbitrariness, because there's no true rest. All right, 1 second. All right, so here he's laying out the rules for clock synchronization, and he's saying that based on the one-way speed of light here, how he's deriving this is that the time for the propagation that would go from T to B would be equal to the time of T prime A to B. So what he's saying there is that because there's a lot of like ambiguity in modern times that you'll be told you can't measure the one-way speed. We don't know the one-way speed. I mean, you can assume the one-way speed because it's, it would work out going that velocity going the one way and then the second way, blah, blah, blah. Well, let's just look at what Einstein specifically defined it as, right? It's going to be equal to the two-way, the one-way trip is going to be equal to the two-way trip. What could that imply, lads? Is it the same speed going back and forth? All right, cool. All right, so just another quick look at that those are going to be proportional. And then we have, let's see, on both sides, on the one way and the two way. So then we have on relative lengths and times. So here we were talking about absolute space and using that for electromagnetic processes. Well, here he's introducing motion to the clocks now, and they're not just two stationary clocks. These are two clocks in motion. And here he shows that there's a discrepancy with respect to absolute space. These clocks will not be in sync when you introduce motion. Now, he's going to tell us how much they're going to be out of sync by. So this is going to be his prediction for relativity theory, right? So this is going to be the introduction to the derivation for link contraction and time dilation. So we're told that so the postulates so far are that all inertial frames are equally valid. So these equations will hold true there, and that the speed of light in a vacuum is constant irrespective of the motion of the emitter or observer. And then, but to mathematically, he shows that that's not true. But to get us back to those postulates where there's a constancy of c in this relationship, you're going to have to do a Lorentz transformation, and as a function of your velocity, as a function of the square of your velocity, you're going to experience physical link contraction and time dilation in your moving reference frame, and it's going in your then that contraction is going to be a function of that of the square of that velocity. So it's going to be a real tiny amount. Right. But as you're moving at these relativistic speeds, it's going to increase. And as you decrease in speeds, it's going to decrease a ton, right? Because it's not a linear function. It's not proportional. It scales hyperbolically based on the velocity going up or down. Okay. So that's in a nutshell, link contraction and time dilation, and then the relationship with velocity. So what he's saying here is that if the clock in motion at a speed nu is fast enough to invoke link contraction time dilation, then in that frame, it'll still be in sync, but it'll be off by just that little amount because of the contraction that the apparatus is experiencing due to the constancy of c, right? So a lot of people will say, well, is link contraction a physical mechanism? They're like, well, it's never been described. I don't know, like blah, 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 right? Well, it has to be a physical mechanism if physical reality is a consequence of the constancy of c. There's no way to say that it's not the physical mechanism, at least in the reference frames that we're measuring it in, where we're supposed to be already contracted. You would have to absolutely argue that it is a physical mechanism. You would have no other way to look at it. It's pretty clear. You would have to just say you're already contracted, so you would never know. All right, and then we get into the physical meaning of the equations with respect to a moving clock. So we talked about clock synchronization and link contraction when you apply that correction for the square of the velocity. So he's going to show us here now where his equations apply and how much this clock is going to be desynchronized due to its motion. So he says, and if a clock at A is moved with the velocity nu along the line AB to B, then on its arrival at B, the two clocks are no longer synchronized. But if a clock moved at A to B lags behind with the other, which has remained by B by 2/2 times t nu squared over c, t being the time occupied by the journey from A to B, it is at once apparent that if the results hold good for the clock, if it moves from A to B in any polygonal line, and also when its points from A and B coincide. So any closed polygonal circuit, okay, looking good so far. And if we assume that the results proved for any polygonal line is also valid for a continuously curved line. And if anyone would like to give a quick shout out on what shape a continuously curved line makes. Quick shout out.
A circle.
Yes. Well, a circle, sure. All right, and then we'll go with circle. So thence we conclude that by bound. So anyway, he just wants to make clear here that he's not talking about, because they didn't have atomic clocks in his time. He's making sure here that we're not talking about a pendulum clock that's swinging back and forth, where he's talking about a light clock. So he's talking about, think about like a ping pong ball, in synchronization with another ping pong table, and they're just bouncing that little bead of light back and forth. That's what he's describing here, and he's saying that ping pong table B, when it completes its circuit, will be out of sync with clock B at this ratio, right? At 1/2 times t nu squared over c. All right. Then we have relativistic velocity addition corrections, just to make sure that the speed of light is never exceeded. We have a little reduction factor there to just make sure that we're always in the confines of relativity and never exceeding it, unless Fresnel drag is involved. Then we can do Galilean velocity addition because reasons. All right. Very cool. So we learned a lot about the framework and the math that's being applied here. But what a lot of people don't know is that the framework that Einstein uses adheres to something called Lorentz symmetry, which is part of a theory that was entirely based on a theory that was put forward by Hendrik Lorentz before 1905 for his theory. And he was using link contraction and time dilation as a physical mechanism with respect to a stationary ether that would physically contract and dilate time relative to the velocity of a moving body going through that stationary ether. And the cool thing about this framework is that when you do a summation of the transformations, you can get back to I call it the lab frame, but you can get back to that absolute space, right? So Einstein was talking about, so what he's doing is he's deleting absolute space from reality with the contraction, essentially, right? And then you could unwind it with a transformation back to the stationary rest frame. And you're like, oh, look, that's how much it would deviate from me if you were moving at this, blah, 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 right? And everyone's like, oh, cool, no way. Well, also, if you do a summation of that, it makes a complete, you could geometrically look at it as a triangle, and that would establish the motion to be with respect to an absolute space. That would enable you to unwind the mechanism of the link contraction and have it preserved with respect to absolute space. So in other words, this mathematical framework that's been thrust upon us through the lens of relativity that explicitly claims to not adhere to a framework that requires absolute stationary space to assign velocity vectors to, has it inherently built in every Lorentz transformation that's ever been done already includes this in it. And you can use it to establish things like absolute simultaneity and a cohesive line of events for clock synchronization, etc. So there, that's cool. All right. Any questions so far, lads? Any cues for the boys?
Tapioca Weasel asked, what does absolute mean in this context?
Absolute means absolute, man. Like exactly what it means. So in relativity, when they're like, oh, it has to be relative to somebody. Well, no, all motion is relative to absolute space and time, right? Because they literally use light to make measurements against it with with interferometers and stuff, which we'll get into. So absolute means absolute.
Okay. So does that mean that there's a frame of reference which is the absolute frame of reference, and there are frames that are not?
What do you mean?
I mean, how would you identify the coordinates of absolute space? I guess is what I mean.
It's a good question. So the way that I kind of would look at it in this respect, right? When we get into the interferometry predictions, when they're doing V over C, you could say that they're using the propagation rate of C in its inertial frame. So they're making the measurement with respect to light's inertial frame, which would be like a conceptualization of absolute space. You could look at it in that way. That would be like a real easy mathematical way to do it for that. Does that make sense?
I'm not sure actually if the idea of an inertial frame for light does make sense actually, because light doesn't have inertia.
Well, it has a speed that it would be measured against, right? Plus or minus. So they've got their induction rate for C that's known as the constant, and then relative to the latitude, they make measurements where it's, plus or minus that. So
relative what latitude? Sorry.
Oh, so you know how Michelson-Gale Pearson 15 degrees per hour, that kind of stuff?
Okay.
So those measurements are made with respect to absolute space. Now they say in this, because it's rotation, right? They say that it's with respect to the rotation of the ball, of the spinning ball, right? But I'm just saying that the speed of light, it has a frame where that speed would be its speed, and then it would be propagating with respect to its material media, right? So here on Earth, there would be an ether wind carrying it relative to its latitude. There would be a velocity difference relative to the lattie, and that's what they measure with interferometry, right? So C has its base speed, and then when it's in a material media, which was proven by Fazal, there's a drag.
Okay, so you're saying that, but the idea of the ether is that you would also see evidence of some contribution to the drag that is not due to the material, as it was in the Fazal experiment.
Yeah. So, for example, when the fringe shifts exceeded the refraction index, like in Sagnac with air, so the velocity fringe exceeds the prediction of like Fresnel drag for air being the mechanism, where the fringe would only be 44% of the velocity with respect to going with or against. And then
okay. I don't quite follow that because the refraction index of air is very close to 1, so I don't know where the number 44% would come in.
yeah,
But
so yeah, no, I got you. So taking it back to Fresnel drag, right? The hypothesis was that the ether was a material media, and that when it interacted with another material media, it would be dragged. And the prediction was a ratio of 88%, 44% going with the velocity, or like going in the direction of the velocity of the material media, and then 44% going against it. So that's what they measured in that. So when I say the refractive index of air, there was a continued history where they were trying to, where they basically continued out the Fresnel experiments. So they used, instead of water, they used mirrors, or like crystals. And then they were like, hold on one sec. And then Sagnac came along and was like, oh, will this work in air? Right. And the fringe shift pattern, like that distance created from that velocity exceeds what would be measured if it was the air carrying it through like a refractive index at that ratio of 44%. Does that make sense now?
Well, the specific number 44% doesn't, but I don't actually. That would be an unreasonable expectation because generally, when you get numbers, like 44%, there's a fair amount of very specific argumentation behind it, which I do not expect you to provide in a few sentences.
Yeah. So it was.
I do have one clarifying question that I think will be helpful. When you say Fresnel drag, is that basically the same thing that was measured in the like Fitsu drag, like when you have a
yes, yes,
media?
Yep.
Okay.
Yeah. It's called Fresnel drag, but it was done by him. Sorry. Yeah, I got some slides later on for that. But yeah, so that's my basis for jumping up. Like when I say light has its own inertial frame, right? So it would have its own speed, which is measured at 1 over the square of epsilon mu, right? So, and then because the ether being a material media that's in motion in our realm, right? There's going to be latitude dependent variation. So it's going to be catching a velocity boost or velocity subtraction going against it relative to the lattie, because a vortex, right?
I mean, I wouldn't have used the word vortex. I was up with you until you said the word vortex, but yeah.
Well, I can show you some stuff, but that's kind of that's what I'm talking about when I
don't want to derail the whole conversation.
You're good. It's super relevant though. So like you're doing great. It's all this, like what we just touched on is actually covered as we continue. So maybe as I go through with the slides and stuff and you see some of the experiments, it'll start to marinate a little better. But no, you're totally fine, bro. You're absolutely on point. All right, so lab frame, and then so Michelson-Morley here. So we got the data set, and this is an analysis done by Consoli. Can't remember his last name, or that is his last name. Can't remember his first name. But anyway, he goes over the Michelson-Morley data. So we have 6 days here where they redefined all of physics over these measurements for the null results, and they say that there was no fringe shift pattern significant, blah, 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 because the prediction was for 30 kilometers a second. So they expected 0.5 of a fringe, or 0.005 of a fringe. And they ended up measuring just over one fringe. I think it was like 0.012 or something like that. But anyway, what this dude does is he does his own analysis of the measurements. He does a harmonic analysis. So what he's doing here is breaking it down, like doing some statistical variation analysis that involves sine waves. So we'll look at those here in a second, and we'll see what his conclusion was. So we're often left in the dark about the air tolerances and accuracy of the Michelson-Morley experiment, but we have Max Born, who went on record here quoting saying that the air tolerances are plus or minus 0.004 of a fringe. So that's pretty cool that we have an actual number here to put to a name to the face, as they say. All right, so now we're going to look at the harmonic analysis by your boy. So what we're looking for here is the sine wave to intersect with the air bars. And we've got some nice intersections here for the measurements. So what this means here is that you can say with statistical confidence, have you ever heard someone say, with sigma 5 confidence, with sigma 3, etc., that kind of stuff, it comes out of statistical analysis. So what he's putting forward here are measurements that are non-zero measurements with statistical confidence that, he uses sigma 3 and sigma 5 for a couple of the different ones. But point being here is that these aren't null readings. These aren't, they're over the expected amount, but they're not what they expected for heliocentrism. I'm sorry, they're over the error margin, but they're not what they expected for heliocentrism. So the rounding it down to 0 and saying that, oh, we can't measure it because relative motion, link contraction, et cetera, was the jumping off point for the solution to this when they clearly made a statistically significant measurement. So here's another look at what that data looks like.
What does heliocentrism suppose should have happened that it didn't match with?
Heliocentrism supposes that they should get a fringe that would correspond to 30 kilometers a second. So a much bigger gap in the fringe reading.
Heliocentrism or no, wait, hold on. Never mind. Ignore what I just said.
You're straight. So this is just what they look like here. So this is what that data is plotted. So just, you can see it nice and clean. All right. And then we have another form of the data graphed out here. So all within statistical significance, but just not what the heliocentric model would require. And then here we have another, we're going to move on to Michelson-Gale-Pearson here. So this is a analysis that the same gentleman did of 10,000 runs of day 1 of Michelson-Gale-Pearson. And this is just an analysis on the min-max of the amplitude of the fringes. So just kind of seeing like, was this noise that was measured, or were these min-maximum dimensions that they're plotting against sidereal time to get their verification of rotation, are they meaningful? And as you can see here, looking pretty sharp from the graph, right? All our min-max fringes are in the required area for statistical significance, as they say. Now we're a quick look at the Lorentz transformation equation. Here, it actually predates even Lorentz's use of it for his ether theory, where he was going to use it for contraction as the mechanism. Well, this dude, Waldemar Voigt, was using it for relative Doppler shift. He uses the Q function here slightly differently. So that contraction mechanism, he multiplies by it instead of dividing. So, but if you divide or whatever, it gives you the link contraction, like in the relativistic sense. And then the other one is, what would it be? Transverse and longitudinal. So one gives you the longitudinal Doppler shift and the other one gives you the transverse. So this framework was already established prior to Lorentz and prior to Einstein, and it wasn't being used for, removing the media and saying that reality is contracting. It was just used to describe Doppler shift, relative Doppler shift. All right, so we got some. I think this is supposed to be earlier in the pres. But yeah, so we got some experimental verification for light. So when people are like, well, how do you know that Maxwell's derivation of 1 over the square of epsilon nu is correct and whatnot? Well, Fazal also did an experiment using a cogwheel rotating at a fixed rate that would flash after it hit a mirror. So he's just basically measuring how many flashes he would get over time with respect to the rotation of that cogwheel. And through timing that out, he got pretty close to the speed of light. I forget what the exact figures were, but that was like the first big one that they used. And then of course the Fazal, dang it, kicked me all the way back. Hold on one second. This new setup's a little sensitive. Okay, cool. So they had their so they're getting close to approximating C here, and then with their predictions and everything, they do the Fresnel drag test, right? So in here, they've measured C, and then now they're using it to start to measure translational velocity. So here in this configuration, they have moving water going through a tube, and they have a split beam that's going to go with and against the water, and it's going to recombine and create a fringe pattern. So what they found was, and they were already using light and fringes to measure refractive indexes and stuff when they talk about the refractive index of stuff and all of that is, basically done with a form of interferometry essentially, right? Because the fringe patterns would correspond to the reduction in velocity for electromagnetic propagation going through it.
What year was this?
Let's see, 18, let's see, one second, pull it up.
Because the wave model of light wasn't basically
Oops.
from the time of Newton until I think Young. It wasn't very popular. So
Yeah.
I thought that you basically had to wait until Young with the double slit and whatnot
No,
before
no.
the wave theory came back, and
N-
I thought that that was roughly 1830, but I don't actually know.
No, so Fazal confirming Fresnel drag was 1851, and then Arago before that did an experiment
That's a
called
super cool experiment. Oh my god, that is so cool.
which
The Arago dot.
yeah, okay, so the Arago dot is what made people abandon the corpuscle theory, because the fact that it recombines like that would only happen if it was a wave. So that really tilted that tilted the balance for a lot of people.
It's this is just a very dramatic story in the history of science. So what happened was that Fresnel, I think it was Fresnel, who was doing his dissertation defense basically for his doctorate in the early 1800s, and on his PhD committee were a number of eminent scientists, whatever, including notably Arago and also Poisson. And Poisson was a big deal because he was
Yeah.
he was Poisson. And
Shout
Poisson
out
was
to
like, this
Poisson.
is an absurd hypothesis that light is a wave, because if it was a wave, then you would expect if it diffracts around a solid disk that you would have a bright spot in the middle. And Arago was also on the committee, and he was like, well, yeah, but have you actually done the experiment? And he did the experiment, and he found that there was in fact a light spot in the middle of the shadow of a solid disk. And it shows you that even the people that are most respected in the community, like Poisson, can just be wrong.
Yeah, dude, that's epic. I did not know the full extent on that. That's awesome. But yeah, they went with, that was pretty pivotal there. So yeah, the prediction here was, anyway, this shows the ratios that they use for this, for the speed of light, shows that they were on the right track, right? Because they're measuring the proportional velocity of the water. So like I said earlier, it was 88% going with, 88% going against. So 44% going with, 44 against, 88% total translational speed measured when you add them together. And they show that with the fringe displacement. So they're starting to hone in on measuring translation. They're starting to measure motion now, right? They're like, oh, this is, what else can we do with this? Where do we go from here? All right, so we have the next step, which I think was, let me follow the notes here. 1 second, so I can get the years right. All right, so we have Oliver Lodge in 1893 with his setup. So what we're looking up here is how he was setting up his interferometer for rotation, and this is his observation box. We'll see the total product of it here. So we have the motor and everything here, 2 spinning discs above to produce our fringe shift, and I think he had cardboard or something to separate the big rotating disc. But what he was doing here was to see if the mass of the rotating disc would produce a fringe shift pattern. In other words, he was looking for a fringe shift based on mass, essentially, right? So this was like the first time they did that, and his results were pretty lackluster. Didn't really work out too well. There was a guy who did them recently on the YouTube channel, Planum88. Highly recommend that guy's YouTube channel. He does a lot of awesome experiments with interferometry and the history of light and all that. Very cool guy. Highly recommend. But anyway, his results were better than Oliver Lodge's, but not significant enough to be meaningful. So then this was done with modern tech and stuff, so more accurate and precise and whatnot. But to move on from that now, after Lodge's experiment, he was like, oh, well, we should keep doing it anyway and see if we can figure it out. But remember, we did have the successful measurement with Fresnel drag. And so carried on by Franz Harris in 1911 was a configuration where instead of using a running water, the media would be glass configured in a octagon around the interferometer, essentially, right? And what he did with that was measure, again, so where he measures the same ratio, 44% basically Fresnel drag again, but this time for a device in uniform translatory rotation, right? All right, so we're going to look at the Sagnac apparatus here, because in 1913, Sagnac came around with his apparatus, and this was the first time that the fringe shift pattern would exceed the fringe shift that was predicted due to the velocity of being dragged through a medium. So in other words, the refractive index of air isn't carrying around the light at the, it's at a proportional velocity of the rotation to create the effect. This is with respect to some other mechanism, right? So this is where you would have to explain this by saying that there was a path link change due to rotation. This is where you would have to start invoking absolute space, et cetera, to explain the measurements, because they exceed the causal mechanism of being dragged with the refractive index. All right, and then we'll come back to this orientation, or we'll come back to the Sagnac device specifically, because he did this, or this isn't the actual configuration that he used. He uses a specific configuration, which we'll come back to the significance here in a minute. But let's just continue on here. So what they're putting forward, what was put forward in 1905 to explain these experiments that were trying to measure the velocity of Earth using light, they said, oh, well, you know what? The fixed point of origin, there's no absolute space for us to measure. So even though in their conceptualization of motion of the solar system, the Earth is going in a circle around the sun, they were like, oh, well, it's an ellipse now. And because it's so big and stretched out, it's actually a straight line. And because if you're moving in a straight line, you're basically in uniform transitory motion. And if you're in uniform transitory motion at relativistic speeds, you're going to experience length contraction and time dilation as a function of that. And so, that's why we can't measure that. So it's the removing of that absolute space. But here we're seeing it's going to have to be brought back for a rotating interferometer, because there's going to be no way to explain the timing difference in the phase going with and against the rotation. All right, so here we're going to look at, so we're told that these interferometers, or before we move on real quick, we're told that these interferometers, that the closed loop circuit measures a specific type of motion. It only measures rotation through angular displacement. So it can't measure like the translational velocity of it. It can only measure the angular displacement. So it can only be like 15 degrees per hour, 14 degrees, et cetera. It can't be like, we're moving at 8,576, or what I mean? Something like that. So that's the way they look at it. And then they say that if the interferometer is configured where the light is moving at a right angle to itself, then that one is supposed to detect linear motion, and that one can't do it because Michelson-Morley. So instead of cohesively coming up with a theory that unifies the measurements, they divided the two apparatuses that are used to make the measurements, and that's how they do it. All right, and then
How?
What's that?
Hold on.
Yeah.
So you're saying that because you don't see a shift from Michelson-Morley, so the argument, as I understood it, of the paper or experiment that you just presented, as I understood the argument, it was that there isn't a translational component to the fringe shift, because a translational component would have been precisely what the Michelson-Morley experiment was sensitive to, and it didn't see a consistent fringe shift with that hypothesis. So instead of it being a translational contribution to the fringe shift, it is a difference in the rotation rate. That doesn't seem contradictory to me.
So they have them explicitly divided up to say that the right angle interferometer doesn't even measure the rotational displacement, right? Because that's what Miller measured. If you look at Michelson-Gale-Pearson and you look at how they plot the periodicity and the min-max fringes, right, against sidereal time to get the sine waves that look all nice and cohesive, that is the same thing that Miller measured with the right angle interferometer. So they never actually measured, there's no difference between linear and rotational motion. But because of the configuration of the apparatus, they've told everyone that this one measures linear velocity, but it can't be done because relativity. And the closed loop circuit measures rotation with respect to absolute space, because if you're in rotation, you're going to have some fixed point of origin for that, outward rotation to be relative to, right?
You're going to have a well-defined, axis.
Yeah.
And in that sense, it is absolute.
Yeah, for sure. So
and I don't disagree with that.
Yeah.
It's not generally what physicists, I think, mean by absolute, but I also think, and this is why my very first question was, what do you mean by absolute?
Oh, so
It's
yeah,
a difficult and a remarkably subtle thing to actually
gotcha. So
precisely define.
So yeah, when they're talking about absolute space, right? It can't be the Earth for them because the Earth is in motion. So absolute space defined by the mainstream is with respect to the stars. So when they say that this, like a local Sagnac device in the lab is rotating, its rotation is with respect to the absolute stars. When they say that it's measuring, Earth rotation, thank you, the distant stars. So when they say they're measuring Earth rotation with the apparatus on the ground, they're saying that the rotation of the Earth with respect to those distant stars is where that absoluteness comes from. But I would just argue that it's the Earth frame. So
Okay. I assume you're very, or at least somewhat familiar with Mach's principle. I find Mach's principle to be a fascinating way of approaching the topic.
I think he was half right. He said that the absoluteness was with respect to the Earth and the distant stars. So he half nailed it.
That's one way of putting it. Another way of putting it is that Mach would say that there is no difference between you swinging a bucket around your head and the universe just on its own swinging around your head.
Yeah.
Which is a much less obvious way of putting the mathematically equivalent idea.
Yeah. All right, cool. So before we move on here, or actually we're gonna move on from that slide.
Before you go, bro, I have a question.
What up, SE?
What's up? We're gonna let them get away with this distant stars being absolute non-motion. I mean, to me, that sounds like a contradiction right there. That kills everything.
Yeah, I mean, like I said, I would argue that the absolute space is the Earth frame, where all experiments have been done, where the laws of physics were derived, where everything has to be covariantly scaled to. So that's where I would argue it. But it's like a philosophical impasse. I'm not gonna not here to make him see it differently or anything.
Okay, I just wanted to point that out.
No worries. So here we got equations that describe motion of the acceleration in rectilinear or circular, right? So we're told, because I'm going to show the configuration here so that it's more clear. But as I was going over earlier, we're told that one configuration measures a specific type of motion and the other interferometer configuration measures the other type. And somehow the universe makes a distinction between the two. So if you're moving in a straight line, the universe has its eyes closed to you. It can't see you, completely blind. You're in Lord of the Rings and you're wearing the ring. Nobody can see you, right? Or however it works, I forget. But anyway, but as we can see, the equations that describe them are all the same. Like there's no distinction. Like how would you ever make a difference here? They're all describing the same thing. Like it's motion, right? There's not, if you look real close, you're not going to see a different kind. You'll see a different symbol here to indicate rotation, but you're not going to, like, where's the difference at? Okay. It's going to be a change in time when it's straight, change in time when it's rotate. Okay. They're the same.
Well, hold on. What's changing in time?
The position.
In velocity, yeah, in one of them it's the rectilinear position and one of them is the angular position. Those aren't the same thing.
So in terms of using light to measure them, they are identical. And this is noted they are, because it's explicitly how GPS works. It doesn't matter if you're traveling in a circle or if you're going in a straight line, you're going to receive the signal with a delay proportional to your velocity. And they don't account for it.
If you're assigning an angular velocity to light, you're not describing its motion through space. You're describing its oscillation in its poorly defined own frame, I suppose. You're describing the actual oscillation of the electromagnetic wave. You're not describing how fast that packet of energy is actually propagating through space. Those aren't the same thing.
Which one of these equations is not describing motion?
Motion is a very general concept. They are all describing motion.
And they're all describing it in the same way, right?
No.
Okay.
The first column, for example, you would use units of distance over time. The second column, you would use units of radians over time. Radians are not a distance. They do not have dimensions of length. They're a pure number.
Gotcha. But it's a displacement over time, right? Because that's really the key factor here. How you differentiate it and want to sector it out based on how you can analyze it mathematically isn't the same. Maybe perhaps I should have worded that differently, but what they're all describing is motion, and there's no distinction between motion, right? It doesn't matter.
The only way that they are the same is when you reduce it to the mathematics. If you actually look at the physical like what you're actually talking about, in one case you're talking about a distance between 2 points, and in the other case you're talking about the angle between 2 lines away from the center of a circle. Those aren't the same thing. Like fundamentally, those aren't the same thing. You use the same mathematics to describe them because mathematics is a very versatile language.
Okay, let me rephrase then. So let's take an observer on the rim of a device versus an observer in linear motion. Now, the angular displacement with respect to the center of the device is going to make that triangle, like you were saying, right? And then the linear displacement is just going to be a straight line. But the important thing to note here is that they're both moving. There's both a change in over time. The universe isn't like, oh, he was moving in a straight line. This one was a circle. Does that make sense?
No.
Okay. Well, I think we'll have to come back to that then, because that's.
Let me try.
Okay.
Is one is just straight motion, linear motion, and one is circular motion. One is actually covering distance. The other one's just going around in circles. Is that correct?
Yeah.
So there you go. Yeah.
Cool.
Okay. I mean, I don't. We can move on. I don't want to. I'm not trying to derail you, Alan.
No, you're good. We'll come back. No, dude. And like I said, I do not mind, because the higher level of pushback I can get, the more accurate I become. So if you feel like I'm grossly misrepresenting something, please jump right in, bro.
For sure.
All right, cool. So this was another look at the old kinematics. So just to recap on what these are describing, right? Change in position over time, change in position over time. Oops. Dang it. There we go. Or maybe I should do it from this one. Okay. All right. So before we look at the Wang experiment, we're going to look at Sagnac's apparatus, his configuration. So earlier in special relativity, it was put forward that any closed polygon.
What? What are you talking about?
Yo, Andrew, you're hot, micing. We were told that any uniform transitory motion, his equations would apply. So if you're in an inertial frame, the speed of light is going to be the same. And as a consequence of relativity, you're going to experience a little link contraction time dilation as a function of the square of your velocity. So what Einstein says, that it doesn't matter that this configuration isn't symmetrical. It can look like this. It's totally fine that the area that light travels makes a non-symmetrical polygon. And as long as it's in uniform rotation, that his equations should apply. So if you were to apply Lorentz symmetry to this, and you put an observer at the center of the device, and you put an observer at the rim, and you said that the angular displacement, due to that motion of the observer along the edge there, is going to cause a fringe shift pattern. Or well, actually, because they're inertial observers, they're both going to predict that the speed of light is the same. So as this apparatus makes its rotation, and because we're not using absolute space to assign for imaginary velocity vectors, we're not preserving absolute space to make the measurement with respect to that. So when this light completes the circuit going with and against the rotation, it's going to complete it at the same time because of the constancy of C, and because the frame as defined by an observer at the rim and one at the center are going to be inertial as defined by Newton's equations and by Einstein's, following that logic, right? Because if you extend any portion of this circle to infinity, it makes a straight line that doesn't deviate much from linear. And that was the whole rationale behind, putting that in the theory, which, logically tracks. It makes sense. So relativity theory actually predicts that there's going to be no fringe shift pattern. And because Sagnac measured a fringe proportional to the rotation of the apparatus, he said, I falsified relativity theory, et cetera, luminiferous ether, optical vortex. When he described the optical vortex, what he was describing and the rationale behind it was he was saying like, the ether must be entrained in the earth. And then within the earth, there's, little pockets where when you're in motion, you're going to create a vortex that's going to be, measurable, right? So that's what he was putting forward with that description there. So on Einstein's terms, he falsified the theory as it was put forward. Now we'll get to the solutions that were put forward here and the history of all that. But this is just to start us off with the first experimental falsification of it, right? And we already talked about the configurations. So a Michelson-Morley interferometer, or the classic L shape, or an orthogonal interferometer, sometimes they're called, or a classic interferometer, etc. Right, is just at a right angle. And they say that this one is for measuring linear motion, but it can't do that because link contraction time dilation. And then we have the Sagnac configuration, which is a closed circle most of the time, but it can be a rectangle, triangle, doesn't matter. It can even be whatever shape this is. It's all good. And it will produce the angular displacement amount, right? And they say that that one's good, but the other one's bad, even though it was experimentally shown in 2004 by Wang that when you have an apparatus and you measure just the effective moving part of it, right, then you will get a fringe shift pattern that's proportional to that motion. So the apparatus is making the measurement with respect to itself. So typically these gyroscopes are wound in a coil around, a fixed point. And then they say, in that configuration, they're like, oh, that's that rotational one. That's the one that measures angular displacement, right? Now, what Wang did is he unwound the gyro, came up with a configuration here where it has a linear section at the bottom. That's what we're looking at. And then it has two sections over here that move. The motion of these two sides cancels out. The bottom part's stationary. And the calculation and the prediction is only done with respect to the delta L, which is the effective length, right? And then, so instead of the full length of the apparatus, it's with just respect to this portion here, just this top part that moves. So some people will say, well, it was with respect to the detector or the station or the bottom bit, et cetera, et cetera. Well, if that were true, then you would have to use the full length of that. You would have to add more length to the L. You couldn't just use the delta L from the top to predict the fringe shift proportional to just that top portion. So he measured explicitly uniform transitory motion, not in a rotation, right? So this is just rectilinear uniform motion. When we're looking at the graph here, where he's measuring the fringe proportional to that velocity, falsifying the postulates of special relativity about relative motion and the constancy of C. Otherwise, the relativity predicts that there's no fringe here. We have an inertial observer here at this end of the apparatus, and he's sitting at the end here. He's an inertial observer, and then we have an inertial observer here, and these two are in uniform motion. So relativity predicts zero fringe for these lads, and if it does, well, the fringe that it predicts with the function of the square of the velocity, right? That gamma factor correction or contraction, sorry. So link contraction time dilation would predict a much, much, much smaller fringe than this. It wouldn't even be possible for that theory to extrapolate the velocity that this was moved at to produce that fringe pattern, because the special theory of relativity is a theory of second order corrections, meaning that they're not going to be proportional to the cause of what's causing the measurement, right? So that first order effect, that velocity would be the first order effect, and that first order effect is measured in full in the fringes here, right? So if this was a second order effect, the measured fringes would be much, much smaller, and that would be an indication that relativity theory is true. But it's not. it's proportional exactly to the velocity. So it's outside of the confines of relativity to provide an explanation. And of course, we have the configuration up at the top where he's doing it with against the rotating wheel on the other side of the interferometer arm. It's just, anyway, my favorite one is the bottom one here, the parallelogram. That's pretty damning. So just to recap here, with the generalization of the Sagnac effect, what Wang is showing here is it doesn't matter if light's at a right angle or a circle, it will measure velocity proportional. So what that means is the measurements from Michelson-Morley stand as first order measurements and not as a measurement that produced a zero fringe and then would require a Lorentz transformation out of it to say, well, the reason you can't measure it is because you contracted by this amount. Okay. So you would think like there's a cohesive history, or that you would think that when a man published a paper of that magnitude in 1913, experimentally falsifying relativity, Einstein would have been all over that to hop in and, and explain this as a relativistic effect. Well, he actually never addressed the Sagnac experiment or the Michelson-Gale-Pearson experiment. I think he went to the MGP construction site, shook the lads' hand, but never commented on it as like a relativistic effect or anything like that. Other people always provided that for them, and we'll get into that a little bit here in a second. But what we're looking at here is a paper in 1993 by Nicklaus, who was doing an interferometer Sagnac setup. And they make note here that there's 22 explanations of people trying to provide a relativistic solution for the Sagnac effect with special relativity. And there's, and among them, there was one for general relativity, which we'll come to in a second. But here, this is just stacking up people trying to explain this phenomenon, right? Because maybe I'm wrong, right? Like I didn't go to higher education. I don't know. Maybe I'm wrong, but all these people here are trying to explain it as a consequence of the postulates put forward earlier, and none of them successfully did so. And we'll take a look here. We'll go through the history of the.
Hold on.
Mm-hmm.
I gotta cut in. So the Sagnac effect is an effect which can somewhat famously be ascribed to a lot of different effects in different sort of frameworks of how you look at the question. Whenever you devise a particular internally consistent framework, you're going to be able to describe the Sagnac effect. That does not mean necessarily that the metaphysical interpretation of your description is going to be identical in every case.
Well,
I would, however, disagree. I forgot what I was disagreeing with.
Okay.
At least I'm honest.
No, you're good. You're good. Well, let's start with the physical fringe displacement, right? Let's forget about the theoretical. Let's talk about what's predicted. So in an inertial frame, those two lads in uniform motion would experience link contraction as a function of the square of their velocity, right? So a much, much smaller effect than what's physically measured. Would you agree?
No. I would agree that it's would I describe that as with the square? I know what you mean. We both understand the gamma factor. It's 1 over the square root of 1 minus v over c squared, the quantity squared. Yeah, so in that sense, but like I think if you actually do the expansion, I'm not sure what order it is off the top of my head.
I would highly encourage you to do the expansion and see what you get. Or
what will I get?
Not anything that produces a measurement that would explain the Sagnac effect, as we'll find, or as we'll find as we continue.
Where you actually don't need to do the expansion, because just doing it straightforwardly, entirely analytically, is computationally efficient. So.
Well, the theory predicts no fringe, though, like just as a baseline, right?
That's
and then
not true.
1 second, applying the link contraction time dilation, which would be, orders of magnitude smaller than what was measured, doesn't explain it at all. So it's not.
Which specific experiment are we talking about? Because I feel like you said multiple things that apply in different ways to different versions of this experiment. And the thing about the Sagnac effect is the base Sagnac effect on its own is somewhat difficult to characterize and like to link specifically without the context of other experiments, certainly, to a particular physical model. You need to have it in context with other experiments. For example, stellar aberration. Like stellar aberration is and I'm sure you agree, a hugely important like
Very
clue
important.
into what's
I'm
going on.
so glad you mentioned it. Well,
Yeah.
in the context of other experiments, which we're going to fully go over and cover, right? Because this isn't even dude, this is just the surface of it. I can't wait till you see the rest of it. This is so awesome. But yeah, let's cover stellar ab real quick, right? So 1727, I think it was, or 2029, something like that. James Bradley had his telescope at his 90 degrees looking at stars. And what he found was that he had to tilt his telescope forward a little bit to keep the starlight in the center of the telescope. And what they found was over the course of a year, if you plot out that deviation from that perfect 90 degree zenny, it comes out to be like 20 arc seconds. And when they ratio that against the speed of light, it comes out to 30 kilometers a second. So they took that as proof that the Earth was in motion. And, you know, it is a nice kinematic measurement, right? And it's certainly, that angle certainly does ratio to 30 kilometers a second. And if I were a heliocentrist, I would be personally ecstatic because that's the only ratio they've ever got that gave them 30 kilometers a second. But I digress. So after that, though, Arago put a covered his telescope with a crystal prism. And the hypothesis was that to sort out the matter on if the Earth was in motion or if the sky was in motion, right? Because one of these implies that the Earth is stationary and the starlight already comes in at an angle, which requires the tilt, or the Earth is in motion and that's the cause of the starlight displacement. So we have two possible theories that angle produces. So to determine which one of these hypotheses is valid, Arago took his telescope and half covered it with a crystal prism. And the idea is that when starlight intersected that centerpiece, he would either have to correct it more or not when it hit that refractive media, right? Because it's going to slow the light down. And then the velocity of the Earth is going to have to be compensated to keep it in the center. So he's going to have to tilt it a little further. He found that he didn't have to make that correction angle. And then a couple years later, Airy came along with what we're told is Airy's failure. But what he failed to detect was the velocity of the Earth. So the hypothesis again was that, you know, to settle the matter of why the correction angle for the telescope is necessary. Actually, I have graphics for this. Give me 1 second. We can do the whole thing. Totally forgot about that. Are you going to
talk about the experiment where they put water in the telescope?
Yep, I'm doing that right now. I'm about to show some graphics for it too.
You see this, chat? This is, you know, people who disagree working together.
Absolutely. Move this over here. All right. Okay. So we have, do you guys see that? Okay. Or did I share it on the good quality or the crappy one? Is it still 1080p, boys?
I see it.
Okay, cool.
It is, yeah. 1080, yep.
Cool, fantastic. All right. Okay, so let's see here. So to settle this matter, right, is the telescope in motion or is the sky in motion? We had two possible outcomes. And so Airy was going to put water in his telescope, and that was going to be the deciding factor. So if the Earth is in motion, when you add water to the telescope, it's going to slow the light down such that it's going to require you to make a further correction. And the predicted amount essentially was 1 arc second per kilometer for the velocity. So if the Earth is moving at 30 kilometers a second, then 6 months out of the year, you're going to have to tilt your telescope forward by 15 arc seconds. And then as it's going in the other direction around the sun, you have to tilt it back 15 arc seconds. That was the prediction, right? So 1 kilometer per, or 1 arc per kilometer, right? For over the course of a year. And what he found was he only had to correct his telescope by 0.8 arc seconds. So there was a slight correction, but not even close to 30 kilometers a second. And the logical implication here is that the Earth is stationary and the starlight already comes in at an angle. So this is, and this is viewed from the lens of putting it on Professor Kinkerfuse's theory that, of a stationary Earth with the Earth moving through it, and then any displacement, you would be able to attribute that to the velocity of the Earth. So that's why it's 15, right? So a stationary ether framework. Now, if the Earth is stationary and there's an ether wind, well, we actually predict there'll be a slight drift, and we could absorb that, no problem. It wouldn't be an issue if there was a medium between the light source and us, and that caused the drift. This would be something that's totally fine. But the problem here for the heliocentrist is that they need to attribute the full velocity to the Earth, right? Because that's what they were looking for, confirmation that they were moving with that first order measurement. All right. Let's see. So did I miss anything on that, sir?
If you do the calculation, and one of the effects, by the way, that you have to keep in mind here is the Fresnel drag of the water. Oh, sorry, you may not have mentioned. Did you mention the version of the experiment where they pour water into the telescope?
Explicitly.
Okay, yeah, that's what I thought. I just want to make sure. That when you actually do the calculation, I don't like which part of it is not consistent with special relativity.
So if special relativity were true and this water is carrying a velocity of 30 kilometers a second, it's going to require a correction. So real quick here, we have one second, pulled it up and then I minimized it. So this is a note from Michelson in his 1887 paper on those results, right? Because you know how we were talking about the undulate or the wave theory and the corpuscle theory too. So this is also a pivotal situation here in regards to that, because he starts the paper off talking about Airy's experiment with the aberration being unchanged for the velocity when water was added. And he says he has a special note here, and then he says, it may be noticed that most writers admit the sufficiency of the explanation according to the emission theory, while it is in fact difficulty of greater according to the undulatory theory. So the wave theory and the emission theory. So the ballistic corpuscle light theory and the wave theory. For the emission theory, the aberration should be less. Hence, in order to reduce its true velocity, we must make the absurd hypothesis that the motion of the water in the telescope carries the ray in the opposite direction. So for the corpuscle lads, they had to say that the light accelerated when it hit the water instead of slowing down, and that's why it didn't correct. And then for the ether lads, they had to say that there was, the stationary ether, mind you, right? But for some reason in the telescope, the ether is carrying the light in the opposite direction of the velocity, and that's why it's creating the illusion that it doesn't, need corrected for. So that was where they were at in the 1800s with that. So I'm not really sure.
Fair point. I was unaware of this. So
yeah.
I will have to look at it and get back to you.
Yeah, dude, it's pretty intense. Like I had a back and forth with someone on Twitter about this, and
there's a lot of paragraphs here.
Yeah,
I'm not smart enough to just do a back and forth.
Oh no, you're good. I'm just giving you supplementary information to follow up on.
Yeah, no.
But this in conjunction with trying to explain this through the relativistic lens is like, it just leads to more problems. All right, so there's no velocity potential carried with this water apparently, opposite or width, and then so that's where we're at with Airy. So we can get back to what's it called? The interferometry stuff. Okay, so let's see the Sagnac effect. It's noted here that Paul Leveuve, that's not how you say his name, but anyways, I'll show you here in a minute. But anyway, this guy in 1917, so a couple years after the Sagnac effect, he shows up and he's like, boys, because the device is rotating, you can't apply special relativity to it. Rotation is an acceleration. And if things are accelerating, you got to apply general relativity to it. So he, using tensor calculus, right, it uses Einstein's new derivations for everything to conserve the rotation of the locally rotating Sagnac device into a gravitational field so that it can proportionally get that contraction stuff. But even that doesn't provide enough because the second, because it's second order effects, it's not going to be enough to be proportional to that, even though there's still, instead of denying the validity of the theory to apply to the frame, now they're like, okay, we'll apply the framework, but we're still in the situation where link contraction and time dilation predict too small of a displacement. So, and then of course you have the secondary issue. It's like, okay, well, suppose we have an inertial observer in the center of the device for the Lorentz symmetry, and then we have an observer at the rim of the device, which is in rotation. Well, we're in the same situation where they both don't predict a fringe shift pattern because they're both inertial observers. So, so they ended up scrapping that after a while, and we'll come back to the experimental falsification to that in 1942 with the Four and Prunet. But that was put forward for a while to put it under the lens of tensor calculus and let the boys transform into it. Oh, Paul Levin, that's his name. Sorry about that. Okay, so now we have some issues here, right? So we've been talking about rotations and who applies to who, because some people nowadays say that, rotation of the apparatus means it's, special relativity doesn't apply, it's exempt, et cetera, et cetera. Well, there's something called Thomas precession, which we'll get to in a second. But before we get to that, to explain the effects of Thomas precession, which is basically they have an electron orbiting around a nucleus, and they say that, because it's traveling at relativistic speeds, there's an anomaly with its magnetic moment or whatever, and it's like precessing a little bit. It's just causing a little wobble or whatever. That's kind of what they say with it. And then to explain that, this guy, Llewellyn Thomas, came along and he introduced a concept called a Lorentz boost, which I'll show the diagrams for that here in a second, but this is to give the history for what Post is putting forward. So anyway, this is under the confines of special relativity, explaining the anomalous electron situation as it has to do with the velocity, right? So it's within the mechanisms of special relativity, right? Velocity. So we're looking good so far. But then in comes your boy Post in 1967, and he's like, yo, check it out. I can explain the Sagnac effect, and I can explain Thomas precession. Here's how we're going to do it, boys. We're going to break electromagnetic processes down into their respective fields, the E and B, and then we're going to put those to a point called free space. Now, I know what you're thinking. There's not supposed to be an ether or an absolute frame that's preferred to be used, but we're dealing with rotation, boys, and times are desperate. So what we need to do is bind these fields to that free space and put it in rotation, and therefore the electromagnetic propagation will conform to the rotation of the fields with respect to that rotating fixed point. And it's like, dang, that sounds like a lot of craziness, man. How'd that work out? Well, a lot of people rejected it because it's not within the confines. It's not mechanistically the same as special relativity. So earlier, Tapioca was touching on the physical mechanism explanation versus the mathematic abstraction of it. Well, what this guy was putting forward, nobody was trying to touch that because what he was doing was essentially using centrifugal acceleration or the centrifugal potential was what he was calling it. Like he was taking that rotation and calling that centrifugal potential, and then using that to provide the contraction of the apparatus essentially. And they were like, yo, dog, that's too close to general relativity, using gravitational fields for gravitational potential and stuff like that. So nobody really went with that. And then Ron Hatch ended up doing the math on this apparently, and this apparently does not predict Thomas precession. But I'm not versed enough in the math to break all that down. But it should be noted there was a big contention there from your boy Ron. And then let's see here. I think so. We're good on that. So back to actually, let me show you a Lorentz boost real quick. Okay. So the idea for the Lorentz boost is that the observer's in it's moving in radians relative to the center point. It's not the same. It's different. Well, what you do with a Lorentz boost is two Lorentz boost is equivalent to one Lorentz transformation. So what they're doing there is they're taking, when you're in rotation, you can have as many infinitesimal, you can break it up into any amount of infinitesimal points as you want for inertial frames. So if you do that and you do that twice, you'll have the equivalence of doing a linear Lorentz transformation. So it'll be, so what he's saying that to explain this rotational effect with an electron, suddenly special relativity applies to that within that framework when it doesn't have to explain a physical fringe or anything like that. Like they were content to apply special relativity to Thomas precession. Now, when you Lorentz boost and you apply that to Michelson-Morley, right, you don't get link contraction and time dilation in the same respect. So it doesn't explain that. So it's just like introducing a coordinate system rotation versus like a meaningful well, it's not meaningful in my worldview, but as opposed to the meaningful physical mechanism of link contraction and time dilation offered by the linear transformation. So it gets into conflicts with that. And then let's see. So Post was trying to, rectify all this and make everything cohesive. But again, it's like when you start going, oh, well, we can apply it to rotation here. Well, then it fails in other places and it's just not mechanistically cohesive. So, we're in, let's see, what year was that? 67. No answer from him in any meaningful way. Yes.
You covered a lot of topics since last time we spoke.
Mm-hmm.
Are you saying that Lorentz transformations or special relativity do not apply if you're in an accelerating frame?
So the argument that was made for Sagnac, and especially when I talk to people about it now, they're like physicists and whatnot, is the argument that they'll put forward is they'll say, well, the device is rotating and rotation is an acceleration and special relativity doesn't apply to accelerations. It only applies to uniform.
Oh, that's wrong.
Linear. Well,
They
I
are
mean,
wrong.
I completely agree. So these are the links I've had to go to.
You and I are in agreement on that. They're wrong.
Yeah, these are the links I had to go to figure out like who's right. So
no, it's actually a very common misconception that accelerations are not applicable in special relativity. So in special relativity, what is required is that, like, as I understand it, and like I could be wrong, okay? I'm not the world's authority on relativity theory by any means. But as I understand it, special relativity applies when the space, the physical space, X, Y, and Z, not time, not space-time, but when space is flat. Which means equivalently that any triangle that you draw between 3 points in that space will have an interior angle that sums up to 180 degrees. That's like one way of identifying if a space is flat. So you can absolutely have acceleration and you can treat it completely fine. You just do an integral in the context of special relativity, and you can do things both rotational and with linear acceleration or a combination of the two. What you can't do,
dude, no way. That's awesome. No, I'm just blown away. I had no idea. Dude, these people were acting like that was just the craziest thing they'd ever heard of. You can't do it, blah, blah, blah. You're just like, nah, it's just an integral. Okay, dude. That's awesome.
I mean, to be fair, just an integral is if you don't have access to something that can approximate it by cutting it up into a whole bunch of really small, fairly easy arithmetic problems, which is just what numerical integration is. Very useful, very useful. But if you want to show a mathematical identity, it is only a guidepost. It's not going to get you to a proof,
Yeah.
Numerical integration. But
Dude.
integration is fundamentally a very hard problem because you're trying to undo. You have to compute an antiderivative, and those aren't even always well defined. The function f of x equals x to the power of x does not have, as I understand it, a closed form antiderivative.
Dude, well, that's beyond me to know what you're talking about, but that is super interesting, and I will definitely have to come back and look into that, because that's so funny, man. That they're just like, no, it's a different frame, can't do it, can't be applied. You don't know what you're talking about. That's that's awesome.
It's definitely like it's a thing that I have found in, and like you can tell a like competent, really like well-read resource like a textbook. Like some textbooks get this wrong, and the textbooks that like don't get it wrong point it out because they're like, yo, hold up. This is a thing that a lot of people misunderstand, even in physics. So yeah, anyway.
No, you're good, bro. It's awesome. All right, so let's see here. We got where were we at? I think this was, we'll just read here and see what we find. We imagine an infinite, oh yeah, so this is just Thomas precession. So we imagine an infinity of inertial systems moving uniformly relative to the laboratory system, one of which is instantaneously matches the velocity of the particle. The particle is thus instantaneously at rest in the inertial system and thus can be connected to the laboratory by Lorentz transformation. It is assumed that the Lorentz transformation will also be described with the properties, of the particle in the rest system as seen from the laboratory. Very nice. All right, so yeah, that was just further reiterating that despite the claims, you definitely can get rotation in there and acceleration. Very cool. And then, well, you know what's interesting? You mentioned the flat spacetime metric. They actually so you know in general relativity they have the curved spacetime metric and they have a flat one. Well, they'll actually use the flat one to derive that stuff as well. It's like they're already imposing it, you know. They're already going with general with special relativity, right? They already took it to an infinitesimally flat plane in general relativity. That's insane.
You are very often able to derive results from in the limit of small perturbations when you only have to consider the linear contribution, and then like look at that and compare it to observations, which is like what physics is about, and also look at and explore the internal consistency, which would be what mathematics is about, and that will reinforce and then often provide a pathway for a rigorous derivation that isn't based off of sort of mathematical intuitions. A lot of results are first derived from intuitions that aren't necessarily rigorously defined, but a lot of them are then later backed up with rigorous mathematics. The Dirac delta function is a great example. The best example in history would be calculus as a whole. I mean, calculus wasn't well founded rigorously until analysis was thoroughly developed in the 1800s. So
shout out to the boys, Levi, Savita, and something Cabastro. Let's see. Oh yeah, and that guy too. All the lads got together and calced out. Rock out with your calculator out, I think was the motto. All right, so we got the Sagnac derivation here. The displacement in time, or the change in time, the delta t is equal to 4a times omega over the speed of light. So this is just showing the length of the apparatus times the rotation, and over the speed of light is going to give you that angular displacement amount. And this is the classic derivation for it, right? So this is just a ratio of velocity over c to give you the predicted fringe amount. Now, in special relativity, if you took an apparatus that was 1 kilometer long and rotating at any velocity you want, you could never get it to produce, you could never get special relativity, length contraction, and time dilation to produce enough of that to cause the physical fringe that's measured by the rotation of the device. So the point made here was by A.G. Kelly, and he goes into the math over it. I just gave like the truncated version, but what he's saying here is that, due to the magnitude of the second order effects, you are never going to be able to mathematically facilitate that fringe pattern out of that theory, because it's a first order effect that's directly proportional to the velocity, whereas time dilation and length contraction are functions of the square of the velocity. Let's see. And let's see. So surely a hero will emerge and explain the Sagnac effect as a consequence of special or general relativity. Did it ever happen, boys? Well, unfortunately, no. But we did have a quick introduction of the general theory to swoop it up for a little bit. So we're going to cover the brief history of general relativity in Sagnac. So the first introduction to what he calls curve linear, right? So straight, but also curved. And this is the idea that you're moving in a straight line, but reality around you is curved. So unless you could take the perspective of some like God frame, you would see from your reference frame, you would be moving in a straight line. But in reality, from that fourth dimensional perspective, you would be moving along the curvature of something, right? So, and this is where the term curve linear comes from, but, obviously a contradictory term like relativity of simultaneity can't be simultaneous and relative at the same time. So they tried to, and this is a quick look at geodesic. Geodesics are very cool. This is one of my favorite parts of relativity. Whenever I look at relativity videos, I always look to see who has the coolest geodesic path in their thumbnails, and that will be the video that I watch. So this is just what I was talking about earlier. This is us looking at...
I want to reaffirm that and say that I completely agree with that metric.
Nice. So this is the what that curved linear path would look like from the God frame. So here we have a photon in a straight line, but Alan, it's going in a curve. Well, I know because we're in the God frame. But from old photon here, this would just be a straight line. And so this is what this is supposed to represent with curved linear and curved space-time and all that kind of stuff. So we're going to look at the Dufour and Prunet experiment now because, an application of general relativity and acceleration in the rotating frame. So this curved linear situation is supposed to produce a result that explains the Sagnac effect. So in 1942 or thereabouts, some French lads, Dufour and Prunet, got together with a specially configured Sagnac apparatus where the top half is stationary and the bottom half rotates. And it's separated by, 5 centimeters, I think it was, and then 45-degree angled mirrors. So what it's doing is they have a source on the lab wall and a detector on the lab wall, and they also have a detector on the rim of the rotating device. And what they're doing here is they're testing to see if the fringe shift pattern will be translated to the inertial observer on the wall, right? Because there's some contention here that, the device is rotating, so it's a non-inertial frame. And of course, what determines the inertiality of a frame, you could say, so with the recorder being on the rotating apparatus, they say, oh, that's a non-inertial frame, so blah, 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 even though Tapioca already went over, there's ways you could definitely fit relativity theory in there through the special theory. Give me 1 second. Let me get the streams going. They're restarting.
You gave me like 2 more minutes. I was going to be able to completely shut this thing down. I was trying to sabotage you so hard.
Nice.
I failed.
Nice.
Yeah, we just learned that Tapioca here is actually the grandson of Van de Graaff.
Yeah, dude. Shout out to your boy Vandy.
Yeah, no, I've known Alan longer than I think any of y'all.
Really?
Yeah, we met through Pitch Lumen.
Yep. Old Pitch.
Oh, okay. So are you here because you knew he was going to be here, or you just happened to be here?
I just happen to be here. This is one. So I keep this particular channel actually. Currently, it's number 3 on my sidebar. But like everything that's in the top 10, I basically gets equal eyesight from me because I like coming here every so often.
Nice.
So how long have you been a flat earther?
I'm not a flat earther, man.
How long before you become a flat earther?
I like that question.
If I absorb the what's it called? Nah, never mind. We'll not get into that. Anyway, whenever you guys are ready to continue, my stream's good to go. So if we can jump back into it, I can finish this bad boy off. If you guys are still down.
Nah, we're over it.
All right.
Yeah, I reshared it. Yeah, good to go.
All right, cool. All right, so to pick up where we left off, we were talking about general relativity and its application for the Sagnac effect. And then we were looking at an experiment that was done where an observer was fixed to the lab wall, and also there was an observer at the rim of the rotating device. And what they found was that the fringe was measured by the observer fixed to the lab wall. So there's some mechanism, right, that's causing the path length to be fully, or when the path length is increased due to the rotation of the bottom half of the interferometer, there's some preserving aspect of absolute space that's making that inertial lad on the fixed to the lab wall make that measurement to keep that consistent with the velocity of the rotating apparatus. So here's some cross sections of what the light paths would look like with the 45-degree angles. So you guys get a nice visual of that. We got your centerpiece of the axis of rotation. And then the 45-degree angled mirrors to facilitate that up and down translation there. And then here's the worst picture ever taken of the apparatus. And so that's what we're looking at here. Bottom half rotate, top half stationary. Yeah, it's not great, but somewhere in here is a lad fixed to the lab wall, presumably.
I gotta say, I'm looking at this thing. All I see is 3 ghosts that look like they're out of
Yes.
Am I wrong?
No, that's the original Sagnac apparatus is actually 3 ghosts. So you're dead on. So the measurements that were shown from this configuration, the classical theory predicts for a fringe displacement of 0.53 fringes, or 0.053 fringes, and the relativistic theory predicts 0.05 fringes in the configuration with the lab wall observer versus the what do you call it?
Ghost potato observer?
Yeah, versus the ghost potato observer on the rotating device. So for those of you who aren't familiar, but this is an incorrect prediction, right? The inertial observer should always be measuring CSC. There should be no reason that the translational speed was preserved through a measurement of absolute space. That's not supposed to happen in relativity theory. So this prediction is way off here by a factor of 10. And Paul Levov's explanation was, hey man, because general relativity is a theory of gravitation and this device is in rotation, there's going to be that inward attractiveness. This is his rationale for it. Therefore, we have to use the center of the device as the preferred frame for the calculation to be done. Because if you invoke the center of the frame, you can, quote unquote, make the same prediction there. But even though they, even though they don't do that, I'm sorry, they can't do that because, then they're invoking a preferred frame, right? They're invoking a stationary frame to make the correct prediction when the general theory is about general covariance. And this explicitly, should be covered in its, it should definitely be able to make this prediction as is if it's going to follow a general covariance, meaning that it doesn't matter if the frame is accelerating or not, it should still make the correct prediction. And let's see here, unlike what we're kind of half told about special relativity only being applicable to certain types of motion. And
I will take credit for the other half of that half told.
Nice. Absolutely. And yeah, you single-handedly pretty much, you and our boys Solzy, who put together that math for the different types of motion all being the same. So shout out to that.